The second type of stimulation treatment is hydraulic fracturing. Hydraulic fracturing is the most effective stimulation treatment for the tight sandstone formations usually found in older, more consolidated continental sediments. When using this treatment, pumps on the surface create several thousand pounds of surface pressure that are then channeled into the wellbore to break down the formation in controlled fractures. In addition, water that has been mixed with gelling chemicals to increase its viscosity is pumped into the well to help in the fracturing process. In combination with the downhole increased pressure from the pressure pumps at the surface, this gelled water enables the increased sandstone pressure to be evenly distributed across the pay zone, thus enabling further fracturing for hundreds of feet in a more or less horizontal direction. To limit leak-off or runoff into the surrounding formation, polymers are added to the gelled water. In addition, gel in the water makes the water slippery enough to reduce friction, thus lowering pumping horsepower requirements. Once the fracture is extended far enough, a propping agent, often large rounded sand grains, is introduced into the gelled fluid being pumped. Because of the high viscosity of the gelled water, the proppant is suspended evenly throughout the solution as it is pumped out into the fractures. When the gelled water with the propping agent reaches the formation, the proppant first seeps and then packs into the cracks in the formation. When the formation is saturated, pumping is then stopped. As the pressure goes down, the fracture, now with the artificially induced pressure removed and returned to normal pressure conditions, tries to close but is instead held open by the proppant. These fractures, now filled with well-sorted large proppant particles, form an excellent flow path for the oil and gas. The last stimulation treatment is a combination of matrix acidizing and hydraulic fracturing and is called fracture acidizing. It is used to stimulate production in limestone and dolomite reservoirs. Because limestone and dolomite are composed largely of calcium carbonates, they will dissolve in hydrochloric acid. In this operation, HCl is injected at a high enough pressure in order to fracture the formation in a roughly vertical direction. As the pressure of the pumped acid extends the fractures, it chemically etches or dissolves an irregular surface on the sides of that fracture, which leaves a high volume flow channel to the wellbore. Like in hydraulic fracturing, the fractures, with normal pressures returning, try to close when the pumps are turned off, but these etched high volume flow channels remain open. As you can see in this illustration, this fracture changes the flow pattern around the wellbore from radial flow to a much higher volume lateral flow pattern. Before production begins for some wells, an additional procedure called gravel packing may be warranted. Sand, for example, in sandstone reservoirs consisting largely of unconsolidated sand grains with very little cementation, is usually pushed to the surface along with the oil and gas. When produced with high-velocity oil and gas streams, it can erode any steel that it might come in contact with. These grains of sand entering the wellbore act like little bullets blasting into the casing or tubing, wearing away most metallic surfaces it comes in contact with. The continued blasts of these grains of sand can cause the casing to split or can cut through the tubing. Gravel packing is, therefore, used to control the sand from being produced with the oil. Even though gravel packing is expensive and is not completely successful in many wells, it is, nevertheless, attempted on virtually every completion in sand-producing areas. Let's look at the process and the steps involved in gravel packing. First, a wire-wrapped screen is run into the hole on tubing with a specialized packer called a crossover packer. Unlike other packers, the crossover packer allows the fluids to cross over from the tubing to the annulus and back again. Next, the gravel is mixed with gelled water and then pumped down the tubing through the crossover passage in the packer into the annulus space on the other side of the screen. As you can see, the gelled water passes through the interior of the screen, crosses over in the packer into the annulus, and circulates to the surface. Because this large graded sand gravel is larger than the mesh in the wire-wrapped screen, it is filtered out by the screen. Trapped, the gravel drops to the bottom and accumulates in the annulus. Finally, the gravel, working as a barrier, filters out the sand, trapping it in the gravel pack and stopping it from flowing into and through the wire screen. Another approach to controlling sand is called frac packing, used in more tightly consolidated formations. It blends gravel packing techniques with hydraulic fracturing techniques. Using this method, the packing fluid is injected at a rate high enough to build up pressure and fracture the formation. Pumping continues as the gravel is packed into the formation. Just like in gravel packing, its function is to stop the grains of sand from flowing into the wellbore. Even with sand-gravel procedures, sand can still manage to enter the wellbore. To protect against the eventual sand accumulation once production has commenced in these formations, the engineering team uses varying techniques. The first is to install blast joints constructed with extra thick walls. In addition, they may use hard rubber coatings on the outside that can help the tubing withstand the sand's eroding actions. Another method is used in areas where the oil and gas flow stream changes direction. In this scenario, these continual motion changes can cause the valve manifold on the Christmas tree at the surface to cut out at its elbow fitting. A failure of this fitting can cause a dangerous blowout. Where the possibility of sand accumulation is a continual problem, the tubing and surface equipment must be cleaned regularly. For example, when sand settles out of the oil and gas and bridges over the well's tubing, it can completely plug off production. To deal with this accumulation, it may be necessary to work over the well to wash out this accumulated sand. Finally, accumulated sand can also drop out of suspension at the surface and accumulate in surface equipment such as separators. Regular maintenance can help keep most surface equipment working properly. As you can see, sand production and accumulation from these uncemented, unconsolidated sandstone formations require constant monitoring with periodic cleanouts. After having spent a lot of time and money on the well, it is now complete. We have run the casing, we have cemented in the casing, perforated the zone of interest, installed the Christmas tree, the tubing, and packers. For the low permeability zones, we have stimulated the well with acid. We have done sand control with gravel packing. However, we are not finished. We still have the question of the future. How long will it produce? How much will it produce? And how will we develop the rest of the field? In Chapter 9, we will discuss field development and field expansion.